Hello everyone, I'm Guihong. My teammate is Sofia. Today we would like to introduce our reinforced learning project. Our focus is reinforced learning assistant 3D object detection. As we all know, autonomous driving is pretty hot recently. Usually, autonomous driving utilizes LiDAR sensors that continuously collect data points from a vehicle surrounding. The dataset then culminated into a 3D point cloud and is used to train a deep learning network to do the following two tasks. First, locate where is the object is. Second, classify what the object is. In our project, we propose these following two research problems. First, what if our agent can learn which node is important or significant or not within a dense graph representation? Second, can we reduce the data complexity and overall training cost and the inference time by using our agent to assist the learning process? Next, let me introduce our methodology. First, a pointer GNN part, which constructs a graph from the input point cloud. Given an input cloud C, we set a threshold D. We will add a link between 2 points if the distance between them is less than D. Therefore, we could convert a point cloud into a graph G. After the graph construction, we use the graph neural network, or GNN for short, to learn the useful features from the graph representation. We first combine the feature vector of each point as the input feature matrix. Next, we build the GNN by stacking several fully connected layers and the activation function sigma. And the GNN computation contains the following operations. First, node feature updating operation. In this process, we use the fully connected layer as the activation function to get the latent representation H here. And then we use a JSON matrix to do the message passing operation. After we learn the useful feature from the graph representation, we use the detection head to make the final detection and classification. In this work, we call the GNN and the detection head as the backbone network. We use the following loss function to train the backbone network. First, for the classification task, we use the cross interpret between the predicted labels and the ground truth. Second, for the regression loss, we calculate the difference between the predicted location XYZ, size, LHW, and angle theta, and the ground truth. Moreover, we also incorporate a regularization loss to avoid overfitting. To summarize, we will use the weighted regularization loss, cross-entropy loss, and the regularization loss to train the backbone network. After the training with the backbone network, we incorporate the error agent to do the error assistant learning. Our environment here is a 3D point cloud graph representation. The algorithm here is a reinforce. The action here is whether we keep or discard the node for feature processing. The baseline here is the total loss without removing any point. And the reward here is the difference between the baseline total loss value and the loss value after we remove some nodes from the graph representation. To summarize our methodology, we first use the pointer GNN module to construct a graph. Then we use the GNN to learn the graph representation. And then we use the detection head to do the detection and the classification. Finally, we incorporate our agent to assist the overall learning process. Now let's take a look at the results. First, as we can see here, the training of the backbone converges very quickly at the first 20 epochs. After the first 20 epochs, the performance has a high fluctuation. We argue that the fluctuation is because the input data has a lot of noise. After the training with the backbone network, we use the error agent to assist the learning process. As shown in the figures, the error agent is able to learn or converge within 1,000 training steps. And also, the table shows that our method results in a 4% recall improvement, which is pretty significant. Thank you for all your patience. We are looking forward to your feedback.